Greetings and welcome everyone to yet another enlightening class and a brand new week where we are gathered here on YouTube, delivering both practical and theoretical insights that are designed to assist you on your path to becoming a climatronico. This means acquiring the skills to repair any electronic air conditioning board within the climate control sector, even if you have never encountered a board before in your life. Let's go! Arrow 3. We're back with arrows. It's been a while since I talked about arrows, right? I usually alternate the classes here. Error E3. In my perspective, what does E3 signify? It indicates a malfunction in the motor fan. Certainly, I am going to discuss my concept. Indeed, I will elaborate on the E3 error from my perspective. However, I consistently enjoy broadening your understanding and expanding the interpretation you ought to consider regarding the error. Ultimately, from my perspective, error E3 is associated with a fan malfunction specifically concerning the evaporator turbine, to clarify it further for you. And everyone, each air conditioning unit will possess the evaporator fan. Every air conditioner will have the evaporator fan. So every air conditioner can have this evaporator fan motor error. It will be a different error, not E3, as I am not familiar with E3. However, what I instruct you on today regarding this defect, what I elucidate to you today about this defect, what I clarify to you today, you will be capable of applying to other machines. Alright, clear? So, learn today, once and for all, how to master this E3 error, how to interpret this E3 error, how to analyze this E3 error. In my opinion, but also extend it to other models. You will be able to apply what I teach here to other machines, other models, okay? Let's go. I'll put the board on the bench now, not much to explain. The error traces back to the fan, and it is either an issue with the circuit board or the fan itself. That's essentially it, all right? It is either the circuit board or the fan. Let's go. I'll set my camera on the bench and we'll start analyzing this board here. Here I am connecting the neutral phase, all right? A circuit board of the carry evaporator. Here's the fan motor. Here is the display. A simulation is shown. Whenever I pick it up, it could potentially be the fan or the circuit board. If you arrive at the machine, with error E3, fan error. If the fan operates properly, it's one type of analysis. However, if the fan fails to operate, it's a different type of analysis altogether. And I will explain to you. I will disconnect the fan here. And connect only the feedback circuit. All right, I'm simulating as if the motor is not running. I have disconnected it. It is not spinning. Now let's observe what occurs. I will activate it here. I have turned it on. Please take a look at the display. Didn't work. I'll turn it on manually. It remained at 24 degrees, correct? Set to 24 degrees. So it should turn on the fan, but I disconnected the fan. Oh, I disconnected it. It's showing 24. It's as if the fan isn't working, which is a defect you might encounter from the R3. Let's see if the R3 will show up here. Just wait a bit. It does take some time. You will approach the machine, activate it, and carefully observe the behavior it exhibits. All right? Turn it on and observe its behavior. Errore 3. No, so if your machine doesn't turn on the fan, what will the RE3 analyze? Let's take it step by step. If the machine exhibited the RE3 error and failed to initiate, with the fan also not starting, it is advisable to examine the activation circuit. Initially, inspect the fan's capacitor. Alright, this particular one here is a 1.5 microfarad capacitor. You will carefully remove it from the circuit board and measure its capacitance separately off the board. If it measures around 1.2 microfarads, it's already considered low. It should ideally be 1.5 microfarads. It's crucial that it provides the accurate value, because if it's slightly lower, such as 1.2 microfarads for a 1.5 microfarad capacitor, it's already out of the acceptable range and can lead to problems. Therefore, you will need to check the fan start capacitor. It can stop the fan from working. Another task you will undertake is to utilize your own multimeter to accurately measure the fan's coils. This fan that I own is functioning perfectly, therefore I shall proceed to make a modification. To provide you with a basis for comparison, I will proceed to measure the resistance of the fan's coils here. The initial coil measures 309 ohms, while the subsequent coil measures 640 ohms. And an additional coil measures 334 ohms, correct? So resistances are relatively high for a relatively large coil, but you notice that one of them is as if it were two coils together. 640, 300 and something, 300 and something, 370, 330. Then when you add 330 with 307, it equals 640, correct? So you take this reading, check if it's a coil, move the fan, see if it's stuck. It needs to be free like this, loose. If it's stuck, it's because its magnet is broken. It has a small internal board here which I've reached responsible for rotation. But what about the board? It could be the fan, right? Never doubt the fan, as it might be the issue. The best is to swap the fan immediately and check the result. On the bench, we do this right away, replace the fan and see what happens. If it stops showing the error, right? As Endeli mentioned, it happened to me too, and it was just the wind from the capacitor. So it has a lot of effect on this capacitor, yes. Very, very much indeed, okay? Quite an effect on the capacitor. The circuit we are going to analyze, look, this guy here, look, this little 6 here, pay attention. This small number 6 here, it is right here, take a look. This small component here, it is responsible for the activation. He is accountable for the activation of the fan motor, a climate control examination for you. Which is which? The board didn't start the fan. Do you want to know if there's something wrong in the fan circuit, or if it's the microcontroller that's not sending the command to activate? You will locate the driver IC. How do you identify it? It's relatively straightforward. Flip over the board, and trace the pathways. Tracks, look, I have here the fan connector, 1, 2, 3, 1, 2, 3, these 3 pins here, it's the fan. One of them, the first one, comes from the capacitor, see, here's the capacitor symbol. One comes from the capacitor, so it's not the one that activates. The other one, look, comes from above here, it goes through here. I just need to find which one comes from the neutral, as the neutral comes directly, right? Just take the neutral here on the continuity scale for my multimeter. Continuity, I'll find the neutral. Observe, proceed directly here, a gentleman correct, simply verifying. In this instance, this particular pin represents the neutral, a gentleman completed. Therefore, in order to observe the neutral, the middle pin serves as the activation point, correct? You will follow its path. When you trace the pathway from the central pin, I arrived at this location registering 0 ohms. It passes through this coil and arrives at this specific pin here. From this IC I showed you, the output goes to the activation pin. I'm checking from the fan activation pin to the IC and it's showing 0 ohms. 0 ohms means the circuit comes here, goes through this coil and follows the track. Here's the IC that activates the fan. If this coil opens, it stops activating. And then I want to see if this circuit is okay. What do? I'm just going to power it up, okay? My display will turn on here, look. I don't want it to turn on, I just powered it. See, the display's off. I'm using my analog multimeter, switching multimeters here, okay? This test works only with the analog one. Adjust the LED scale to either X1 or X10, and I will proceed to activate the input. Just a moment, let me demonstrate this more clearly. I'll place the fan. I am going to activate the input of this integrated circuit. Observe the capability of my analog multimeter. When I turned it on, it spun, see? It spun, fully activated. Oh, I stopped. Stop spinning. I activated it. It's spinning. I stopped. Stop spinning. I activated it. So, I'm activating it here. I'll turn it off here and show you. I'm activating it. I am currently activating it on the two central terminals located here. The black probe on this second pin, the red probe on the third pin, I already know, I've studied this guy before. I know these two pins are input pins. If you don't understand it, what's written on it is AKH223. You take this, type it on the internet, and find the pin out. If I do this, if my motor spins like it did here, it means that this whole activation circuit is okay, but it didn't turn on the fan. Could it be the fan? It could. She didn't change the fan. It was the same way. So what could it still be? Pay attention to this here, because only someone who works in maintenance will tell you this, right? Please pay close attention. Pay close attention to this particular point. When you activate it and the motor turns, the motor is fine, the activation circuit is fine, but it's not engaging, it's not turning. It could be something between this little IC here that I showed you. It might be between the IC and microcontroller. Yes, maybe. There's a trace here. Follow it to check continuity. Could it be open? Yes, it might. However, it also occurs that the microcontroller fails to activate the fan. And that's correct. What do you mean, Lawanda? The microcontroller not activating the fan is correct? Exactly. The microcontroller is the brain of the board. It is intelligent. It exclusively activates the motor, specifically the fan, only when there is alternating current voltage present. It meticulously reads the alternating current voltage. It meticulously reads the alternating current voltage, and when it attempts to read the alternating current voltage but fails to do so, it does not activate the motor, specifically the fan. Sometimes the circuit is fine, everything is okay, but the microcontroller won't send a signal due to no AC voltage reading. There's a circuit that reads the AC voltage, correct? On this little board here and on this board, just out of curiosity, the one that reads the AC voltage on this board is this little white optocoupler here. It is the one that sends the AC voltage signal to the microcontroller. This little white one here is the communication. Here is the inverter, right? Here is the communication. And this little guy here is the feedback. It's the AC voltage signal, the AC voltage reading. If this guy is bad, if any cycle of this is bad, it won't send the signal to the fan. All right? With this, you now know how to activate the fan with an analog multimeter. Now you know that there is a circuit that goes directly through an AQH2223, which is an IC that activates the fan. For those who know, it is an optotriac. You can activate it directly. If the fan turns on like it did here, the fault isn't in the front, it's between C and the micro. Sometimes it's just a trace or a resistor between C and the micro. You will thoroughly check and follow the trace leading to the microcontroller. If everything appears to be in proper condition with continuity all in order, if continuity is indeed in order, you should remember that there is an AC voltage reading circuit that could potentially prevent the microcontroller from functioning properly, from activating the fan. Because the microcontroller does not activate the fan if it doesn't have the AC voltage reading. Right? So that's the activation part. Folks, this applies to my idea. It applies to any evaporator, right? The circuits are the same. So extrapolate this logic and apply it to other circuits. All right, class, is the activation part clear? The activation part is this circuit here. Connector, capacitor, the AQH module, the actuator mechanism, and the microcontroller. And the alternating current voltage measurement, correct? Here it is. We are in this little circuit here. The washer, it turns on, activates. Let's do the other analysis now. And folks, this analysis is for any evaporator. Now the next analysis is as follows. I will connect the power part and I will disconnect the feedback, the rotation sensor, okay? I will disconnect it and leave it loose. I'll connect the board here. And let's observe how it performs, shall we? At this point, I will activate it manually. It's currently set to 24. There it is. Let's see if it'll turn on the fan, okay? We have to wait. We need to wait. We must have patience. Please wait for the machine to operate and observe how it functions, all right? Oh, it turned on the fan. I'll leave it here on the side because it keeps moving around on the bench. Look, it moves like this. See? It goes back and forth. See? It's spinning now. See? And it's not reading the rotation. Notice that when it's like this, without reading the fan's rotation, it doesn't lower the fan's speed. It speeds up and stays fast. It'll remain this way until the error happens. This is a particular behavior. Pay attention, man. This is a behavior where you activate the machine. The fan initiates and it doesn't decrease its speed. It doesn't modulate. It remains at its maximum speed, indicating that the board isn't receiving any feedback. There's no feedback signal present here. Where I connected it, it might be the motor not sending a signal or the feedback circuit, you see. It displayed the error code E3 once more, and now the fan has ceased its operation because it failed to rotate. What observations will you make in this particular situation? Defects. It could be an issue with this small internal board. There's a small board here. It might be faulty. I won't open it since the cable is tied up tightly here. I won't open it, but you can remove it here, take it out and check the board. Analyze it, try to fix this board. It can be fixed. It has a Hall sensor on it. Alternatively, you have the option to trace the connector located here. This is the connector associated with the fan feedback circuitry. This particular connector in this location requires both power and a signal. I will proceed to trace the signal here promptly. It is feasible to trace it swiftly in this area. Just to see what's in this circuit, come with me here, I'll explain it to you. It won't be perfectly clear, but you'll see me doing the tracing here. The battery goes here. Come here to the trail. She arrives from that direction over there to this location, crosses over, descends, and then arrives here. All right. From this point, it proceeded over to that location, correct? Observe, here it arrives. It passes through a resistor. I'll explain, then show you. It passes a resistor, then a diode. And from the diode to the micro, the diode is just a pull-up. So I just pass it to a resistor. Is that right? If I just pass it to a resistor in series, what should the resistance be? Certainly 5K ohms is accurate, whether it is 5.0K, 5.1K, or even 5.1. Yes, precisely. There exists a diode in this location that is receiving 5 volts. So please verify this particular diode here. This diode ought to be connected to the 5-volt source. 5 volts followed by a relatively small pull-up diode. It serves as a reference point. Okay, see? Look at how I trace the circuit. I'll disconnect here to get it close so you can see. Here is the connector, all right? The trio of pins on the connector. The trio of pins on the connector here, observe. The trio of pins on the connector, all right? It arrives here, proceeds over there, subsequently it traverses to the opposite side, emerges here precisely at this tiny location, proceeds through this resistor here, makes contact with this pin here of the diode. This diode here possesses 5 volts on this side, serving merely as a reference, and it proceeds to the micro pin, all right? Thus, from the connector signal, the signal arrives, reaches this resistor, traverses through the resistor, and subsequently reaches the micro. Here, it serves merely as a reference diode. The significance of this diode is that it provides a reference for this micro pin. However, if this diode is malfunctioning, or this resistor is open, or this solder is cold, this signal will not reach the micro, resulting in a signal failure. In this scenario, I intentionally induced the defect here. I disconnected the signal from the connector. However, if you have the connector connected and that diode is leaking, or that resistor is open, or that trace is open, or the solder is cold, failing to establish proper contact, this might inhibit the signal from reaching the micro, which will cause the IR3, all right? Let's measure voltages. What are the voltage levels? What do you expect and see? What do you expect to analyze here? I will connect the fan. I will turn it on again. I will turn the board over. Because I'm going to measure. You're going to take the board and measure the voltage level. DC. From this board, from this pin, from this point here. So grab your multimeter. Set it to DC voltage scale. And what voltage do you need to measure when it is rotating? I will energize it here first. I have just energized the component, but I haven't activated it yet. And I am going to measure the voltage levels here with great caution because the part is currently energized. I will measure solely the voltage levels from one terminal to the other, which are 12 volts, and purely out of curiosity, on the middle pin, it will oscillate, correct? I am going to rotate it here manually and just hold it right here with my hand and observe that it remained at 7.4 volts, rotate it again slowly, and it dropped to 0. This is a test, please pay attention, a test of the black motor rotation sensor. You will need to take the multimeter probe set to the DC voltage scale, energize the board, but refrain from turning it on, just energize it. Place the black probe on the G and D of the feedback pin. Here I have three terminals, G&D, VOUT, and VCC, which are the three feedback pins from the signal originating from the motor. Touch the black probe to the G&D and the red probe to the VOUT, the pin that transmits the signal to the microcontroller. I touched it here. I am measuring the DC voltage and I am going to rotate the motor manually. Rotating the motor manually, at a certain point, it transmits the signal at 7.42 volts DC. If I rotate it a bit more, this signal will vanish, returning to 0. So I rotated it a bit more, 7.4 volts. Rotate a bit more, 0. It can be 5, it can be 12, 7.4 because the supply here is 12, right? The supply for this board here is 12. The supply is 12 volts. So my pin is giving from 0 to 7. If the supply is 5 volts, it can be from 0 to 5 volts, 0 to 2.5, 0 to 3 volts. But there will be a voltage between 0 and 12 on this board here. I want to check if I turn it and nothing changes, no point alters the VOOT voltage, it means this motor isn't sending a feedback signal. It's a great test, practical and simple to check if the motor at your client's place, even in the field, sends a signal. 7.4, I rotated, it didn't send a signal anymore. So I rotate it swiftly by hand here, and it will provide a voltage ranging between 0 and 0.7. If I stop at 1.0, I can turn it a bit more, and it stops at 7. This shows there's a signal indicating the motor sends a rotation signal. I'll now turn on the board. I'll turn it on now. I have activated it. She'll start the engine soon. We'll see how it goes when it rotates. The voltage stays fixed here while the engine runs, as the main point is to observe the fixed voltage. It rotated. It stopped already. Why? Because it's getting the feedback, right? It already rotated again. It rotated again already. It's normal for it to stop, okay? For it to rotate and decrease, see? I will rotate it here. 3.6, 3.74, it is oscillating. Do you see? Why is that? Now it is experiencing the rotation. Notice it's rotating. It started oscillating. It's normal for it to stop on the bench, see? This is normal here, okay? Fantastic, welcome. You've become a very important person here. Excellent, happy learning. It's been oscillating. Do you observe the tension? It will continue oscillating. Observe what? Without feedback, it would just keep speeding up. Remember, it was speeding up non-stop. Now it speeds up, slows down, speeds up, slows down. That's normal behavior. From the motor, no E3 error, but a communication error will appear soon, though it takes a bit longer to show. And pay attention, at max rotation it stays around 3.6, 3.7 and fluctuates, okay? So, look, the behavior of the fan is important, the feedback voltage is important for you to interpret. With this lesson here, man, pay attention to what I'm teaching you here and you'll get ahead of most of the market. You will now proceed to interpret the behavior of the fan. Please go to the machine, switch it on and observe its operation. It came back, turned on, accelerated too much, oops, no feedback. It sped up and modulated. Oh, it's okay. It activated and the fan oscillates, speeds up and slows down, speeds up and slows down. With the turbine, it's tough to see, right? It's more complex with the turbine. Now you even know how to measure the test. Turn off the machine, turn off the control, right? Keep it energized, measure the voltage from the G&D to the feedback, rotate it and see if the feedback oscillates. If it doesn't oscillate at the feedback, at the VOT pin, the pin that sends the signal to the microcontroller, then the motor is faulty and not sending a signal. Notice, class, a lesson like this isn't just about the E3. It's relevant to any model with a black motor. Clear? Therefore, there's rotation and it's showing a fan error. The fault is in the circuit. If there's no oscillation, the fault is in the motor. There's oscillation, the fault is in the circuit. If it starts working right, it starts working, there's oscillation at the pin, but it's not reaching the microcontroller. The microcontroller isn't reading the signal. In the minority of cases, the defect will be in the microcontroller. In the minority of cases, the defect will be in the microcontroller. So stop blaming the micro when the defect is in the fan, okay? Great, class. Is it clear? Error. Error E3 on Midea is under control. Under control, okay? Under control. That's it. There's no way around it. It was E3 on Midea. That's everything I told you here. What did you learn today? How to thoroughly test the fan drive circuitry. Identify the issue with the capacitor at the fan pin. Analyze the operational behavior of the fan. Engage the fan circuitry utilizing an analog multimeter. Learn that if it doesn't turn on the fan, it might be the reading and what voltage it should be. Few people know this. Few people who know this are my students. And now you all know, right? And if the fan becomes operational, I analyze its behavior. If it speeds up too much and doesn't slow down or oscillate, it's because feedback is missing. To know if it's missing in the fan or on the board or reaching the microcontroller, I go to the feedback terminal block, the feedback signal, which are 3 wires, VCC, GND, VOUT. Not in the sequences can change, okay? This is important. The sequences can change. Here it's GND, VOUT, and VCC. Then you will look for the VCC first. VCC will measure, you will find either the 12 volts or the 5 volts. If you find these 2 pins here, this one is the vote. If you find these 2 pins here, the middle one is the vote. If you find these 2 pins here, this one is the vote. First look for the VCC and GND. Attention, it's either 5 or 12. If you find the 5 or the 12 and the multimeter reading is positive, it means the black probe is the GND. Keep the black probe and only change the probe to the VOUT. Power the board and manually spin the motor. If the signal varies, the motor sends but doesn't reach the microcontroller. Trace the circuit, follow the path, locate the resistor, diode, and capacitors that might block the signal from reaching the microcontroller. It's that simple. Folks, this circuit is simple. When you don't know it, it seems like a headless creature, but now you know it. Watch this lesson several times, as many times as you want, until it clicks for you and you interpret this circuit in a masterful and professional way, like a climatronic. All right? Great, everyone. We're really in this together. Thanks to everyone who's here. Leave a like if you enjoyed this class. Awesome. We're in this together. May God bless you abundantly. Sending a warm embrace. Thank you so much, my dear friend.